Every single day in the United States, 40,000 people, almost enough to fill Research Stadium to capacity, receive a nuclear medicine imaging procedure that uses the radioisotope technetium-99m, or as it's commonly called, Tech-99m. Picture that, 40,000 people every day. That's more than 14.5 million per year, heading into medical facilities all around the country to have their insides imaged. But Tech-99m doesn't just grow on trees. Not even here in the land of Doug firs. Nope, it takes a whole different kind of beaver to produce and harvest this resource. Oregon State beavers, to be exact. From the College of Engineering at Oregon State University, this is Engineering Out Loud. Hi, I'm Jens Odegaard, your host. There are 3 beavers, that's the Oregon State mascot in case you're from out of state, that I'll introduce you to in a minute. But first, let me set the stage. This season on Engineering Out Loud, we're sharing stories of how our researchers are helping us stay healthy and safe. Tech-99m is incredibly important for nuclear medicine imaging procedures because it's the industry workhorse used in 80% of them. It's an ideal medical isotope because it can be used in a broad range of applications. It's commonly used to image bones, the brain, kidneys, lungs, and the heart.
The real beauty of technetium-99m is that you can attach it to many, many different kinds of molecules.
That's Steve Reese, director of the Oregon State Radiation Center and an associate professor in the college's School of Nuclear Science and Engineering. He's the driving force behind Tech-99m production at Oregon State, something that's never been done at the university level.
Famously, it's used in what is called a stress test, which many people will probably be familiar with. The idea is that you run on a treadmill, you inject the technetium-99m, which is attached to a chemical, then you place radiation detectors around the body and you look to see how the heart moves the blood. And you can see like blood flow, blood volumes, condition of valves. It adds a lot of fidelity and a lot of information for a physician.
The problem is that the Tech-99m supply is bottlenecked, with the entire U.S. supply being imported from overseas. To understand why, we have to jump into a quick technical and historical lesson. You with me? Tech-99m is actually a decay product of the element molybdenum-99, or Moly-99 for short. That is to say, Moly-99 turns into Tech-99m as it emits radiation. So, to get Tech-99m, people make Moly-99. This Moly-99 is then shipped to medical facilities, which have instruments that, and I swear this is the actual term, milk the Tech-99m from the Moly when a patient is ready for the procedure. Now here's the kicker. Moly-99 is traditionally made in large nuclear reactors that generate an enormous amount of neutrons.
Traditionally, and currently, Moly-99 is made in about 5 places around the planet. And these are associated with rather large reactor facilities in terms of research reactors.
So to make the Moly-99, you put a uranium-filled container, called a target, into one of these large nuclear research reactors, and then bombard it with neutrons. As the neutrons hit the uranium fissions, which makes a variety of daughter products, one of which is Moly-99. The sole North American producer of Moly-99, Canada's National Research Universal Reactor, stopped producing it in 2016 and shut down completely in March 2018. Even before that, it suffered shutdowns in 2007 and 2009. These early shutdowns caused a bit of chaos.
So this created a crisis in the Moly community because they were making at the time about half the world's supply, and certainly more than half of the U.S. supply.
This obviously left a gaping hole in the U.S. market. Enter Oregon State. Tentatively, even doubtingly, at first.
And it was about that time after the crisis abated a little bit that I was approached by a group asking me if trigger reactors, like the one here at Oregon State, could be used. And the first time they came in, I said, no, the reactor's too small.
Let me interject. Oregon State's trigger reactor can operate at a maximum steady-state power of 1.1 megawatts. Or to put it technically, a heck of a lot smaller than the reactors traditionally used for Moly-99 production. Reactors like the 80 megawatt Canadian reactor. Anyway, back to Steve.
And they said, okay, thank you very much, and went away. And they came back a second time. And they said, well, is it possible to use it? And I said, well, yeah, but the problem is we don't make enough neutrons. Neutrons are proportional to the size of the reactor. So if you're too small, you can't make enough. And so they went away, and I started thinking about it. And that's when I grabbed Todd. And I said, all right, so...
Todd is Todd Palmer, a professor of nuclear engineering here at Oregon State. And basically what Steve said was, Todd, since we can't make more neutrons with our reactor, can we make a better target? If you'll recall from our earlier technical lesson, the target is the container that holds the uranium that fissions to make Moly-99. And what did Todd say?
And we looked at this target design, which is very, very simple. I mean, incredibly simple. And just seemed to beg for a little innovation, you know. It's just like, hey, it's a can. It's a can that contains a layer of uranium in it. Well, all right then. Maybe we could do something a little bit better than that.
They embarked on a journey to design a new target that would both increase the number of neutrons hitting the uranium and also use low-enriched uranium rather than highly enriched uranium as the fuel source. Highly enriched uranium can be used to make nuclear weapons, so you can see why low-enriched uranium is the option of choice for university research reactors. To start on the target design, Todd and Steve borrowed a concept from industry.
There were things that had been done in the commercial industry over the years where people had figured out that with a judicious use of water rather than more fuel, that you could actually get more neutrons into a target. We thought, well, what if we, instead of having water only on the outside of the target, what if we had an annulus where we had water flowing through the center of this tube, an annular tube, and you got just lots more thermal neutrons coming into this target as a result.
This idea seemed pretty good, so the next step was to start computer modeling some designs. This is where another member of our Oregon State community enters the story.
I am Medican Monk. Right now I am a postdoc at the University of Illinois at Urbana-Champaign at the National Center for Supercomputing Applications. And when I was at Oregon State working on this project, I was an undergrad student researcher.
At the time, she was getting ready to start her junior year and had been doing some work with Todd.
When I came on the project, Dr. Palmer and Dr. Reese told me a little bit about the design that they were interested in optimizing. And then what I did is I performed parametric studies to figure out what design we needed to come up with that would make the most moly in the limitations that we had. So I played a lot with the thickness of how much material we could have, how much of the fuel material we needed to make the moly. But I also came up with lots of other crazy ideas. I would propose them and they were kind of my own. And of course, I wasn't exactly sure what I was doing, but I would name them these crazy names like the Tiger design, and then try and pitch them to Dr. Palmer and Dr. Reese. I have no idea what you two thought of that.
Medican, I remember that Tiger design now.
It was a double annulus.
Yeah,
do you
correct.
Remember?
Yeah,
stripes.
And I remember thinking, how on earth are we going to build this?
Yeah.
I mean, okay, look, I was having fun with the mental ideas, but I was not thinking about if it was feasible at all.
Though the Tiger didn't roar, Medican's work was crucial in optimizing the target design as she simulated hundreds of design iterations.
There's lots of different variables that we have when we're optimizing these different targets. And so I got to do my own experiments and play around with it and see the effects of how the design change affected our target and how much moly we were making. And that was something I really enjoyed doing. It was really just this fun sort of mental playground that I got to be on every day. So I didn't really even think of it like work. I was really just having a good time.
Through this experimental work, the team honed in on a final target design. Now back to Todd Palmer with a valiant attempt at describing what the final design looks like via some not-so-helpful anatomical metaphors.
What is it? It's about as long as your arm, and it's about this big around, about as big around as your eye socket. I don't know.
Okay sign?
Yeah, about an okay sign. It's yeah, you're laughing because I said the eye socket. And you can't see my okay sign out here. But yeah, and how thick is that? Is the annular region? I don't even remember exactly how big that is.
It's pretty thin.
Yeah.
But the whole thing is, the whole diameter is only about 1.5 inches.
Yeah. So this is not real big.
To recap that whole digression, the target is a cylinder about 2 feet long and about 1.5 inches in diameter. The low-enriched uranium is sandwiched between 2 layers of metal cladding. In the center is an annulus, or tube, that allows water to flow through. It's this water-circulating annulus that's the key to the whole design. Because, as we discussed earlier, water increases the number of neutrons that hit the uranium, causing more fission and thus producing more Moly-99. In fact, through more validation experiments conducted at a national lab and funded by grant money, the team found that they had struck gold.
And we came up with this design that seemed to suggest that you could make commercial quantities of moly in a reactor as small as 1 megawatt like we have here at Oregon State University. And the reason why that's fairly profound in the moly production community is that you go from maybe 5 facilities on the planet to upwards of probably 30 to 40 reactors around the world. So you could essentially take the reactor and it would no longer be a bottleneck anymore.
The target designed by the team here at Oregon State can be used in almost any small research reactor.
Each reactor is unique, but the beauty of it, these targets are such a size that you can put it in not only trigger reactors, but also plate-type reactors as well.
The plate-type reactors that Steve mentioned are another type of fairly common research reactor. The whole design and idea is so promising that Steve, Todd, and Medican patented the technology.
Yeah, and as a matter of fact, the patent application went in and was filed, and then shortly thereafter, a company formed, Northwest Medical Isotopes, to license the technology from the university and to go forth and try to mature the concept.
Maturing the concept basically means setting up the whole process for getting the moly to market. First of all, once moly is produced in a research reactor, it must then be processed or separated from the uranium at a facility.
And this is not something we'll be doing at Oregon State University, but the ultimate endpoint is that you have to remove the Moly-99 from not only the uranium, but all of the rest of the radioactive constituents that are in the target. And then once you separate the Moly-99, you make sure that it is of the purity that you need, and if it isn't, you purify it. And then what happens is you take that Moly-99, usually in a liquid, and you, for lack of a better word, sell it to a company that then puts it in a form that can be injected into the human body.
Northwest Medical Isotopes is full steam ahead with plans to commercialize this operation. They're moving toward building a processing facility in Missouri, which is an ideal central location for shipping moly to medical facilities around the country. The ultimate plan is that research reactors across the United States, including the trigger reactor right here at Oregon State, would use the target design to produce moly, ship it securely in lead-lined containers to the production facility, which would purify the moly, and then send it wherever it's needed. If all goes well, and so far it has, production should start up sometime around 2020, breaking the bottleneck and impacting thousands of people in the United States every day.
It's just around the corner.
Cool.
As for us, at this point, the handoff's happened, right? And we're just hoping to see it come to fruition.
If, or hopefully when, it does come to fruition, it will mark a huge success for the role universities and their researchers play in benefiting both our everyday health and well-being, and in developing industry-ready technology. This episode was produced and hosted by me, Jens Odegaard. Audio editing was by the talented Moly-99 Ayton. Our intro music is The Ether Bunny by Eyes Closed Audio. You can find them on SoundCloud, and we use their song with permission of a Creative Commons Attribution license. Other music and sound effects in this episode were also used with appropriate licenses. For more episodes, bonus content, and links to the licenses, visit engineeringoutloud.oregonstate.edu. Also, please subscribe by searching Engineering Out Loud on Spotify or your favorite podcast app. See you on the flip side.